Hello, I hope everyone is doing well. I am not available right now. I had to pop back to the UK, so I am magically coming to you from the land of Monday, where I'm just going to record this talk, mainly for the reasons that it gives me zero accountability. I can say what I want, no one can challenge me, which is a nice situation to be in. So this is going to be my data tribe talk on good map, bad map. Just an overview of maps in general. What is a map? Sounds stupid, but it's actually an interesting question. I also want to look at coordinate systems, what makes a map good, bad, and how we define that. Well, let me get stuck in. The motivation for this data tribe talk was a Slack thread that I saw. It was a very interesting thread. It was all about kind of map quality, base map quality at Unicast. And it was a very interesting thread. One comment stood out very strongly to me, which was this one. But if we could replace the map with a better one, that would be great. It's a little embarrassing to have bad maps as a location data company. And that two words, bad maps, is absolutely fascinating to me because I think it demonstrates quite substantial misunderstanding on what a map is and what is a bad map and what is a good map. So in this session, I'm going to talk a little about good maps and bad maps and why there is no such thing as a bad map. There's also no such thing as a good map. And I'm going to talk a little bit about why that is. And the aim is that by the end, hopefully we all kind of have an aligned understanding of maps in general, kind of the concepts behind them. And hopefully it's somewhat interesting. So let me start with a bad map. This is a map from the Atlanta Falcons. They traveled to London, the American football team. And it's kind of fascinating. It was famous for being a bad map. If you have a look, they've kind of numbered 1, 2, 3 on the journey, suggesting that they kind of stop at these positions. But somehow they're saying they take 3 planes to London, and they kind of name those journeys which go back from London to Atlanta, despite the numbers going up in 1, 2, 3. What's even worse is that if you have a look where London has been labeled, they've managed to put it in Barcelona. So the question is this a bad map? The answer is, oh yes, it's a bad map. It says that London is in Barcelona. That's the bad map element. There's some other aspects, the kind of the labeling, the diagrams are inaccurate, but they're not necessarily map features, but the map itself is bad. What about this map? Is this a bad map? Yes, obviously. They've managed to say that Hong Kong is in Brazil somewhere. This is on CNN, an American news channel. I initially gave them the benefit of the doubt, and I assumed that they are actually talking about the Antipodean point. Because on this graphic, it's a revolving globe, I assumed that they'd labeled Hong Kong on the back of this globe. See, and they just took a screenshot at the point where it rotated, so it seemed like Hong Kong was overlaying Brazil. But if you look at the Antipodean point of Hong Kong, it comes out in Chile, just in the middle of the ocean. So no, they just got this wrong. Is this a bad map? Yes, this is a bad map. Hong Kong is not in Brazil, therefore it's a bad map. Okay, what about this? This is a map that's probably really obvious what it's showing here. As everyone is, I'm sure, shouting at the screen, this is a map of Saudi Arabia drawn purely by its rivers. Obviously, the joke here being Saudi Arabia has no rivers, has no permanent rivers, and therefore this is a map of Saudi Arabia and its river systems. So the question is this a bad map? And the answer is categorically no. This is a perfect map. We didn't say that we wanted to map Saudi Arabia. We didn't say we wanted to map country borders. We said we wanted to map Saudi Arabia by its rivers. And this is a map of Saudi Arabia by its rivers. So now we start to ignite the debate. What is a good map and what is a bad map? Because in reality, this is a perfect map. This is a really very good map. It shows exactly what is described and exactly what we wanted to see. Here's another example. This is a map of all Tesla charging stations in the year 1507. So is this inaccurate? No, it's accurate. This is a good map because it's true. In 1507, this is what the map of Tesla charging stations looked like in Europe. So is this a good map or a bad map? It is a very good map. So now when we talk about good maps and bad maps, something that often appears would be something like the Mercator projection. Here is the Mercator projection, and I know everyone knows about this already, but I'm going to go through the points. Sorry if you know all of this already. The Mercator projection is a way to take a globe a 3D surface and put it onto a 2D plane. In this case, a piece of paper, for instance. If you want to map the world onto paper, because the world is obviously it's kind of roughly a sphere, it's not a sphere, roughly a sphere, then you're going to have to make approximations. And the Mercator is one such approximation. Obviously, the problem being that if you take a look at scale, you can see all of these circles are supposed to represent the same area. But as you go north or south on the Mercator projection, you change your latitude, you'll see that that circle expands or contracts, and therefore scale is not preserved. So there is I'm going to go through some points on this one. There's a brilliant website. I really recommend going to it called The True Size. And this website essentially allows you to take polygons of countries, move them around, wiggle them around, and see what they are, the true size of it is according to the Mercator projection. An example, the famous one is Greenland, right? Greenland looks huge. It's at the top of the map. If you put it next to India, you can see they're roughly the same size. Obviously, India is huge as well. But if you get them to move India over Greenland, suddenly India looks so much bigger. You know, it's this kind of, it seems that there's a huge difference when you look on the map. In reality, there isn't. One of my favorites is putting Chile over Europe, which stretches from kind of North Africa all the way up to the far Norwegian Sea. I mean, Chile is a huge country, but it just doesn't seem to be on the Mercator projection because it's nearer to the equator than Europe is, which is a problem. Indeed, and one final example, if you take Iceland and project it over Niger, they appear to be the same size on the Mercator projection, but in reality, of course, Iceland is far, far smaller than Niger. So it's kind of, it's a big problem here in scale. So the question is the Mercator projection wrong? Is it a bad map? Well, here is the kind of the adjustment to scale. You can see that there's a huge difference. If you look at Russia, it changes massively. Or if you look at the DRC, it changes barely at all. And this is considered a weakness of the Mercator projection. Is it wrong? No, the Mercator projection is absolutely right. It's a very, very good map. The reason is it wasn't created for showing the size of the country. That wasn't the reason for it. It was created in the 1500s as a means for sailors to navigate the sea. The reason being because sailors used what's known as a rum line. That's rum as in R-H-U-M-B, from the Greek rhombus, meaning direction, not the drink. A rum line is a really interesting piece of marine navigation. The idea is if you had a sailor going from, for instance, Portugal over to the West Indies, if you were to take a great circle, which is this blue line, that would be the shortest path. So you can see on the Mercator projection below that appears as a straight line. Because that's the shortest path one can take. Sorry, no, it's the other way around. The red line is the great circle. So that would be the shortest path one could take across the globe. If you take the blue line, however, that is what's called a rum line. Now, what this means is if you plot it on the Mercator projection, it's a straight line on the Mercator. Because in Mercator, the angle and direction of two locations is preserved perfectly. The idea is it's a lot easier to take one bearing on your compass as you leave Portugal and follow that bearing all the way across the sea until you reach the West Indies. If you took a great circle, it's supposedly shorter, but actually you have to adjust your bearing constantly as you're going, and then you end up making small mistakes, and that's going to take a wiggly line. It ends up actually taking longer. So sailors use a rum line, and that's what Mercator was built for. It wasn't built for looking at country scale. It was from getting from point A to point B across the Atlantic Ocean at the end of the day. The problem is that we've now propagated it into modern society where we're not interested in rum lines, and suddenly all of these other problems crop up. So as a result, we have, of course, 1,000,001 geographic projections. Here's just a few of them. Which of these are right and which of these are wrong? Well, it doesn't work like that. Every one of these is correct and every one of these is incorrect. Each one of them will have a purpose. It was built for something. There's a great projection that preserves Antarctica. It preserves the scale and distances in Antarctica, but everything else is just kind of rubbish, absolutely awful, because it's used for Antarctica, you know, and that's not useful in another projection. So it's a really good projection in that one case, but a really bad projection in other cases. There is no good projection. Every one is an approximation. And there is no bad projection because every one of them is an approximation. Actually, having said that, there is one single bad projection, which is this one from XKCD, where it's an equal area map apart from Greenland, which uses Mercator, and therefore is officially a bad map projection. This is one of XKCD's bad map projections. He has a bunch. I recommend going to find them. They're very funny. So we talked a little bit about map projections and how they are all approximations at the end of the day. Now I want to talk about country borders and how they relate to these projections, and then on top of that, how we use coordinate systems. So I want to start with this example. This is a map of Bristol in the south of the UK. On top of it, I've drawn the postcode lines. So all these polygons represent postcode areas where kind of people are gathered together into a single postcode. So let's zoom in to an area. So if we go from this lower left panel, we zoom in a little further, and we zoom in even further to the coast. And what you can see is this yellow line here marks the edge, the boundary of the UK, essentially. And it does a really good job. Look how tight it is to kind of these this black area here, with the blue area being the sea and this black area being the land. And it fits really, really nicely. Or does it? No, of course it doesn't. It's awful. If we then look at it in a satellite view, this is what it looks like. This is exactly the same scale. It's this picture here. And here is the beach. Look at all this land it's forgetting. Now, usually you define the boundary of a coast as the average point between the lowest tide and the highest tide. But this is Bristol in the UK. This is constantly shifting these sands. So every day the sediment will be different. Every day the tide comes up to a different point. How do you define these? Well, you can't. It doesn't work like that. They've tried to approximate it here. So this is the border that they've approximated, but it's wrong. It's as simple as that. This is the best that someone could do, but it is wrong. It's wrong according to reality. It's wrong according to the satellite view here. It's just incorrect. This, of course, then calls into play what's known as the coastline paradox, which is a bit of a tangent, but I just want to go into it. I'm sure lots of you know about it already. The coastline paradox is this idea that if you start with a low resolution and try to measure the coastline length of a country, you'll get one value. And then as you increase that resolution, suddenly the coastline length increases. So an example here, when the animation restarts, you'll see that we start at a resolution of something like 150 kilometers. And if you take that resolution, then the coastline length of the UK is around kind of 3,000 kilometers. As you're increasing this resolution, you can fit better and better to these little inlets. And suddenly the coastline is now at 10,000 kilometers. So it's 5 times as long. And don't think that it plateaus anywhere. It just keeps going. Eventually you fit to all the bays and the inlets, and now you're fitting to the rocks on the cliffs, and then you're fitting to the sand in between them. This is actually an example of a Sierpinski fractal. The idea being that if you look on the bottom, these fractals increase in surface area, whereas and the area within it is undefined. And that's what you see with the coastline. You're constantly always going to be increasing in resolution and therefore increasing in length. And so what do? How do we define that? Because every polygon that you have that defines the shape of a country has a resolution. It's got a minimum length of one of those edges, and that's what's been decided as the length of the edge. And that's going to give you one value for the coastline. It's going to give you one approximation of the coast. So as soon as you take polygon of a country's border, it's wrong. It's as simple as that. It's just wrong. It's never, ever going to be right. The only way it could be right is if you're down to atomic level, and even then it would be changing, every nanosecond. So it's never, ever going to be right. It's always going to be only an approximation. So I want to talk a little bit about coordinate systems and how these relate to these polygons that you see on borders. So if we start with this coordinate system here, so this is the one that most people are familiar with. This is called the WGS, or the World Geodetic System. I don't know if I've said that right. It's something like that. Now, it should be noted that this is not, it is unrelated to a map projection. What you see here is the Robinson projection, and this is the most common way that you would see WGS represented on a map. Obviously, it just deletes most of Antarctica. It cuts part of Alaska or Russia in half and gets rid of the North Pole. It's a projection, but it shows what we would use as lat long. It's what GPS uses and all of that. And it seems really awesome. It seems fantastic. We use it day to day, but it's got massive problems. So the way that the WGS works is it tries to find the center of mass of the Earth. It then projects from the center of mass of the Earth outwards until it reaches the surface, and then it defines that surface point as a point in space with degrees of arc from that center of mass, starting usually at Greenwich, but there's different standards. And the way that this is done is they try to approximate the shape of the Earth using its gravitational field. So they've done that from space, they've done it from ground surveys. The problem being that all of these give different measurements. If you do it from space, you're going to get a smoother example. If you do it from the ground, you're going to get a much more bumpy example, but it's also going to be a worse resolution because you can't cover all of the ground so easily. So there's many, many standards of WGS. So yeah, this is if you see kind of if you stand here next to this mountain over here, your gravitational pull will actually be pulled sideways, and so a ground reading would give a different reading from space that would look at this whole area in general. Hopefully that makes sense, but just the point being there that it's not going to be perfect, but it's what we use day to day. There is another one that's also commonly used, less commonly than WGS, but we see it a lot. I know lots of the UK data uses this. This is UTM, Universal Transverse Mercator. So this takes the Mercator projection and it breaks it up into cells, into squares. And all of your coordinates are defined as east or north from certain points in these cells. And the cool thing is you can zoom into these cells and break them down further into cells and further and further and further. The idea being the further you zoom in and the smaller the cell you use, the less the distortion from the Mercator projection. And so this works really quite nicely on small areas. It also allows you to define your own system. So most countries will actually define their own UTM just around the borders of their own country. This also has its flaws. So let me break down kind of the advantages and disadvantages of both. So WGS, lat long is easy to understand. We all know how it works. It's kind of the world standard. GPS uses it. Everyone uses that. Problem is, it's hugely distorting in local areas. So especially around the equator. So this is a map of the Earth with exaggerated kind of extremes of gravitational field. But you can see it's very, very lumpy. WGS generally doesn't describe this very well. There are plenty of local coordinate systems you can bring in, but then you're moving away from a standard WGS. They try to approximate it as a spheroid, an oblate spheroid, which doesn't work terribly well. So locally, very imprecise. It's also hard to use if you want to calculate the area of somewhere using these coordinate systems. I know there's loads of Python packages, but actually the maths behind it is fairly complex. It's not something you can kind of do in your head. UTM, on the other hand, is locally very accurate. So if you take a tiny area, for instance, a city, UTM is far, far more accurate than WGS because you can understand distortion far less. Distance and area is easily derived. You can literally just use geometry, like simple triangles and squares, very easy to use, and it preserves angles and shapes, which WGS doesn't. On the other hand, when you get the discontinuities at these boundaries of cells, it suddenly becomes difficult because now you're calculating in negative values as well. It becomes a lot harder to use. There's many, many, many standards. I showed you the Mercator projection of UTM. You can also have UT and then whatever projection. There's so many. And over large areas, it just doesn't work very well. Suddenly, you're bringing in the errors prone to that whatever projection you're using. So that's just kind of an overview of the two big systems and why they're both terrible. Yes, I just want to go on a tangent here because I think this is fascinating. Just this week, there was an article released on this blue patch over India where there's this low gravitational field. This has been known about for a long time. Nobody's totally sure why it is. Until this week, there was an article published where there was this theory that actually this is where a planet hit our Earth. It's well known that there must have been a planet that hit the Earth, and all the debris that came off from the moon, which is now floating around the Earth. And they think this is where it happened. This is where the collision is. And actually, there's probably debris that is still sinking in the core. And the density differences are causing this low gravitational effect. Totally unrelated to this talk. I just thought it was very interesting. Okay, so back to the coordinate systems. You got WGS, UTM. So one works for big areas, one works for small areas. So what happens when you take the United States? The United States is a big area. So let's take the border of the United States according to one of the polygons I've downloaded. This is from the Department of Defense. It's a fairly low resolution view of the borders, but it's pretty great. Look at it. You can see the Canadian islands over here. You can see all the little islands. It does a pretty good job of drawing the US. Anyone who saw this just on its own would know from the shape, it is the US. This is defined in WGS as is standard. So what happens when you take a small region? Here's the border between the United States and Mexico. And look, suddenly we're dealing with a small area, and yet we're still using WGS. And this is what we just talked about, that it's going to be bad. It's going to be ill-defined compared to something like UTM. But we never convert. You're never going to convert to UTM for these smaller regions. Also look at the way that it's approximating the coastline. Also consider that although this is a man-made point, it's got a margin of error in terms of the degrees of freedom. The decimal places on lat and long will not necessarily be correct compared to what it was originally. So this can lead to really big problems in terms of how you're looking at small areas using a polygon. An example would be this is the same, in blue is the same polygon I just showed you, showing the US-Mexican border. And I've projected it onto Kepler, which most people use. And this red dotted line shows you where the true Mexican border is. Now, what I hope people are shouting at me right now is, which one of these is wrong? Is it Kepler? Or is it the Department of Defense polygon? Well, as I hope we've established, they're both wrong. And there is a huge issue here that people will take a polygon, project it onto some display, whether that's kind of a Carto, whether it's Kepler, whether it's Google Maps. Each one of these have their own small differences in projection. Everyone has converted them back and forth a million times. Decimal places would have been lost, rounded, increased, and so there's always going to be differences. And as we've established, neither of these is correct, and neither of these is wrong. So even though they're showing completely different answers for where the Mexican border is, there's no way of saying which of these is correct, or certainly which one of these is better, especially when you consider that these errors compound. So actually the true answer is going to be neither of these. It's going to be a far more accurate value on an atomic level that is in between these somewhere. So which is better? Neither of them. What's even worse is then if you take a satellite view. This satellite view is obviously taking square images, which are a real 2D picture, almost certainly therefore represented in UTM, and yet they've just been shoved on top of WGS system. This is kind of accounted for when you zoom out and you see the different resolutions of the satellite view. That's just going to kind of paste over these WGS systems, but it's always an absolute mess. So you can see that actually this lines up, this red line here actually lines up very well with the Kepler version of where they say the border is. Most likely just because they've forced that to happen, because these satellites would have been satellite views would have been shifted, such as there's certain points of alignment. That doesn't mean it's right. It's two coordinate systems that have been mashed together, almost certainly incorrectly. That's just the way it works. So yes, so going back to this kind of point at the beginning, in terms of, it's embarrassing to have bad maps as a location data company. In my view, it's embarrassing to say that a map is bad, and it's embarrassing to say that a map is good. If we were a company that said we have perfect maps, then I would be embarrassed. I think it's really incredibly dangerous to have that kind of worldview. A map, by definition, is an approximation. So it can only be to some degree correct. Furthermore, if you don't have a definition of what the map is showing, then it's always going to be incorrect. Let's go back to Saudi Arabia's river systems. At the end of the day, that was a perfect map because it showed exactly what we wanted to show. So that was a depressing overview of how everything's wrong in the world of geospatial data science. So let me leave you with something a little more interesting. This is the Mappa Mundi from the year, well, approximately 1300. And this is one of the earliest medieval maps of the world. And I hope you can clearly see that it's a map of the world. Of course, the world at that time, according to the medieval Europeans, was just Europe. They didn't really know what was outside of that. What's really cool is you actually have the east at the top here. which obviously is where we get the word orient, and therefore orienteering, orient meaning east, because maps always used to be towards the east, because they're often created by the Germans, and the Germans would look east towards the Holy Land. And that's what you see at the center here. They've got all sorts of fantastic things that don't exist on this map. But here is what is Turkey at the end of the day, in the Middle East, and then you've got but you can see the UK stuck on the side here. You've got kind of Germany, there's Spain down here, the north of Africa. This is actually India over here. People kind of suspected India existed, heard stories, and there was some trade, obviously, but not too much knowledge. So if anyone tells you that your map is bad, I think we just reproject all of our coordinates onto this map, and we start working off the Mappamundi instead. I think that would be far more interesting to work with. Okay, I hope that was interesting to you, and I hope that that was at least vaguely useful. If you have any questions, I can't answer them, so sorry about that. Please email me, maybe, and we can have a chat sometime. I love talking about maps. Okay, that's all from me. Thanks very much.